About this one here, 64-bit assembler, essentially just follows what I did in the lecture, and this is a new project I just added because of a student question. A student tried to do ED202, and they found when they did the first buffer overflow here, where you put in some stuff and you're supposed to see segmentation fault, they got stack smashing detected. And they said, why am I getting that? And I said, well, you're probably not using exactly the version of Debian I told you to use, and whatever you're using, might be Ubuntu or something, is turning on some extra defenses. And it occurred to me that I didn't have a project where you explore these defections on Linux, the kind we saw in OllyDebug on Windows. And so I put that in, and it was kind of fun to put in. So here we can talk about ELF binaries, which is what Linux programs are, and how you detect their memory defenses, which is important to us. So I put in the same old vulnerable program we've been using for a while that has a buffer overflow, but we don't really care about exploiting it now. I just care about finding out what the defenses are. So when you compile it with no special switches at all, just raw GCC, then of course when you run it, it asks you for a password and it tells you fail, but what we care about here is the defenses. And there are a couple of old programs to detect defenses, and I found some online sources complaining that there are some advanced defenses that these scripts won't pick up. So this is not the most modern, most thorough list of defenses, but it's a place for us to start. So Hardening Check is one of these scripts, and you can just put it on, but you have to install dev scripts to get it, something developers are supposed to get. And when you run a hardening check on a compiled binary, it will check for 5 things. Position independent executable is, of course, whether you can relocate it in memory, so address space layout randomization will work. So these are stack protections, which I thought would be the Canary, but I think it's only checking for a particular other stack protection, but something to prevent the stack buffer overflows we're doing. Fortifying source functions doesn't let you use things like string copy, but only string ncopy. It prevents you from using the 10 or so most dangerous string routines. Read-only relocations means you cannot write to those relocation records that we were attacking in, say, the Windows exploits, where we attack the C library relocation points. And this immediate binding is something similar, something about binding 2 libraries at compile time or something. So again, it's difficult to hit the relocation records. So these are the 5 things it checks for. And so there's another one called Check Sec, which is even more detailed, gives you more detailed information about it. So here it tells you whether the relocation records are read-only, whether it has a stack canary, which we've talked about before. It's a random number added to the end of the stack to detect if you have been overflowing a stack variable and hitting the return pointer. You can't do that anymore because when you hit the stack canary and modify it, the operating system will notice that and stop instead of letting you continue to execute code after corrupting the stack. You can still do an overflow from one variable into another, but you can't get it to the return pointer. And here's the not executable bit, showing whether it honors that. Here's the position independent executable. I don't know what our path is actually, or run path, I forget. I think I saw a description once, but I forgot. And here's symbols. This is another thing. You could strip symbols out of your code, which makes it harder to debug, and it means you won't find as much information when you run strings and such. So anyway, these are 2 tools to show you all these things, and there's some online documentation. I warn you, it is much more confusing than you might think. A lot of the instructions you find here don't actually work, partly because nothing is ever exactly the version you think, and partly because everything is more complicated than it seems. There are several different types of stack defenses, like when you put a canary on, this one will detect it, but this one will not detect it because it's looking for some other stack defense. So this is just the beginning of a complicated can of worms. But anyway, I thought it's a good thing to go through, and so I just gave a series of challenges here where you had to figure out how to turn these various defenses on and off. You have to figure out how to control the position independent executable, how to control the canary, how to get rid of symbols. So your code will not have as many strings, and it won't have labels for things like routines and variables to make it easier to debug, and therefore easier to reverse engineer. And I found an entertaining bunch of online websites. Some of them say you could have source stripped symbols of everything before you write and distribute code. And the other guy says, you're out of your mind. You leave symbols in everything because otherwise you will go out of your mind when it's time to debug them. And they say, well, for large code, the symbols actually make it like 5 times bigger. And other people say, it doesn't matter how big it makes it, you got to have them. So anyway, these things are all areas of hot debate. And so here I figured out how to turn on this Fortify. And when you do, it complains about some of these commands. Didn't stop me though, but it didn't like me using fgets, which is one of those dangerous commands that gets something from the user and copies it without worrying about the length of it. And then I figured out how to turn on this immediate minding thing. So anyway, that's extra credit, of course, but you might want to go through that, and you might want to compare it to the defenses we saw in Windows programs. Does the stack canary require processor hardware support? No, it does not. It's all in software. And on top of that, by the way, in Windows, I know, and I think I also saw it in Linux, it doesn't turn it on all the time. You can choose with compiling switches. The default switch to turn it on will only turn it on sometimes when it decides that the stack appears to be at danger. Like if there is a string variable in the stack longer than a certain length or something. It'll decide, oh, this looks like something that might overflow, and we'll turn it on here. The default stack canary is not always on, although you can tell it to always use a stack canary. And the same thing's true of Windows. If you turn on stack canaries in Windows, they don't really appear in every routine. It decides which routines look dangerous and turns it on. So apparently, stack canaries are considered to be expensive and waste extra memory and overhead, so that for performance, they don't like to just turn it on all the time. Anyway, and you can also see one of these, you strip out the symbols and you can see how much smaller it made the program and such. So anyway, it's good to start doing this, and each one of these is like an area where you could research it quite a lot more. So it's good to see that. Anyway, that's what I wanted to show you.